There are quite a few systems in physics that oscillate or undergo repetitive or cyclical motion. Think about this mass attached to a spring on a horizontal surface. If this surface is frictionless and we pull the mass a little bit to the right and let go of it, what's it going to do? The spring will pull it back towards the equilibrium position to the left. But as it passes through the equilibrium position, because it has inertia, it's moving, it wants to keep moving, it's going to go to the other side. And eventually the spring will stop it and then push it back towards the equilibrium position. And the box will oscillate back and forth about the equilibrium position of the spring. And if there's no friction or air resistance, it'll do that forever. This is cyclical motion, repetitive motion. The box started out over here. We stretched it a little bit until the spring was stretched to some maximum amount. We let go, and it moved until it came to rest on the other side. And then it moved back to the starting point. So it completed one cycle. And then it goes back, comes to rest momentarily, turns around, goes back. Now it's back where it started again, completing its second cycle. And it will just continuously go through these cycles. So cyclical motion, repetitive motion, oscillatory motion, those are all words for this type of motion. Let's take a look more carefully at the governing equation here. It's Newton's second law. Because our object is only moving in the horizontal direction, the normal force equals the weight, they cancel out. Our net force is just the spring force acting on our box. If we pull the box over here to the right-hand side, so x is positive, the spring will be pulling it to the left. So the spring force will be in the negative x direction. If x is positive, the spring force is in the negative direction. F equals negative kx when we're looking at a spring vector equation. And we know that the acceleration is the derivative of the velocity versus time, and it's the second derivative of position versus time. So I can rewrite this as the second derivative of position versus time. Now, what do I mean by x here? What I mean is a function of time. What is the position of my object, my box, as a function of time at any given time? This is a function of time. And I want to know what that is. How can I write this function? My equation is telling me that I'm going to take two derivatives of my function with respect to time, and I'm going to get negative a constant times my function back. What function do you know of where you can take two derivatives and you get negative a constant times the same function? Any sine or cosine function. A cosine function, you take two derivatives, you get negative a constant times the cosine function again. Same with the sine function. We could use either one here. I'll use a cosine function. This is the most general form because a cosine function can't be more than 1 or less than -1. So I can multiply by an amplitude here to tell me just how far my spring is stretched or compressed. If I stretch my spring by 2 meters and let go, x has to be 2 meters at t equals 0. So that's where this amplitude comes in. I can multiply the amplitude by the cosine function, and I can make x be whatever I want. I'm not limited between -1 and 1. This is for fixing my initial conditions. We already said we could have picked a sine function instead of a cosine function. We all know that we can turn a sine function into a cosine function by adding or subtracting pi over 2. So this symbol is there to help us fix our initial conditions. So if x as a function of time is equal to this function, a cosine omega t plus phi, then I take a derivative with respect to time. I should get my velocity. And I take a derivative of cosine function, I get negative sine function, but there's an omega in there that's going to come out. And if I take the derivative of this, the second derivative of my position versus time is going to be the derivative of my velocity versus time, is going to be my acceleration versus time. And you can see we're getting back to where we started. We now have negative, a constant, times our original function, x of t. So my formula up here said, I take the second derivative of x with respect to time, I should get negative, a constant, times my original function. And what is my constant? It's got to be equal to k over m. This is a mass on a spring. So k is the spring constant, and m is the mass of the box. We can get cyclical motion for other things. We can get cyclical motion for a pendulum, a simple pendulum swinging back and forth. We can get cyclical motion for a physical pendulum, right? A rod like this going back and forth. That's a physical pendulum. We can get cyclical motion for other things. And in certain cases, we would also get this relationship where the second derivative of my position versus time function is equal to negative a constant times my original function again. When do we get that? Whenever the force is proportional to the displacement, like it is here with the spring. The force is negative kx. Anytime we have that situation where the force is proportional to the displacement, we end up with this relationship here. Second derivative of my position versus time gives me negative a constant times my original function back. Now the k and the m are specific for a mass and a spring. The spring constant is k, m is the mass. If I have a simple pendulum, I'm not going to get a k and an m. I'm going to get other things there, other constants, but I will have a similar relationship, and I can use a cosine function or a sine function to describe my position versus time. There are many forces that are more complicated than this. They're not proportional to the displacement. And those are much more difficult to solve, the differential equation. In this case, because we get this nice relationship, we knew that a simple cosine or sine function would solve this differential equation. We call this simple harmonic motion because it's very easy to solve this problem. Most problems in physics are a little more difficult to solve, but this is nice because it has a simple solution. So let's talk about what some of these symbols are. First thing is that capital A, that's our amplitude. That's the maximum displacement from the equilibrium position. Omega is our angular frequency. And that's equal to 2 pi radians times f, our frequency of oscillation. The units are radians per second. F is our frequency. That tells us how many cycles our mass completes in a given amount of time. Cycles per second or a minute or whatever our time unit is. Usually we use seconds. And of course, cycles isn't a unit. This is just 1/seconds, or hertz. Hertz is the same as 1/seconds. We also have the period. Capital T is the period. And that tells us how long it takes our box to complete one cycle. That's the number of seconds per cycle. So the units are just seconds. And because the period is seconds per cycle, and the frequency is cycles per second, you should see the relationship there. One is the inverse of the other. And the last thing is that phase angle, phi. What's that for? That helps us set our initial conditions.